So that's me. I've been in the storage business for a long time, working on mostly on distributed file systems. And I joined ScyllaDB a little over a year ago, where I'm leading the storage team in the software development organization. And this opportunity, I would like to also say thanks to Rafael Carvalho, the developer that done most of the work on incremental compaction. He can't be here. His wife is expecting. She's 9 months pregnant, and she's about to have a baby. So he's with us in his spirit. And also, I would like to thank Nadav Harel, who's done the early research work and is responsible for the design and architecture of this feature. All right, so as an introduction and a general overview about the way we store data in Scylla and the way we compact it, I'm going to talk about log-structured storage and then the fundamentals of compaction. So first, what is log-structured storage? How do we use it for writes? So we start with changes to the data that are coming down the wire over CQL, usually. And the first thing we do with them is we record them in memory, in what we call mem tables. We also store them in a write-ahead log, what we call the commit log, but that's a little bit out of scope for this presentation, so I will not talk about that. But the next interesting step is we flush the data from the mem tables down into SS tables. And then updates to the data accumulate over time across these SS tables. So say we wrote, I don't know, A to some cell. It will be recorded into one SS table. And then at a later time, we write B. Then we may have a write of A in this SS table and a write of B in another SS table. And we need to take that into account. Now, having several versions of the same cell being stored is called write amplification. The SS tables themselves are immutable, meaning they are written once, and they are never rewritten. They contain the changes to the data that we also call the mutations. Another aspect of SS tables is that they are sorted, and this is where they got their name from, as sorted strings tables. And they also have, in addition to the actual data, they have metadata like index, statistics, and filter data that allows us to query the data efficiently. Now remember, as a note, that there is no static view of the databases. So unlike, say, relational databases that keep the actual information in tables on disk, we only keep the changes to the data. That means that for reading the data, querying the data, this requires reading all the relevant SS tables that may contain pieces or updates to the data. And then we apply those live mutations, those mutations that are not TTL'd or not overwritten by other mutations. We apply them onto our cache, and that's the way we get the form, the final form of the cells, the rows, partitions, and so on. Now we use the Bloom filter to locate the relevant SS tables. Now doing this consolidation process, consolidating these mutations, is pretty expensive because we need to access the data, access the disk several times, and do the consolidation in memory. And this is called read amplification, because we will need to read multiple SS tables in order to form like a single row. So to summarize, why is compaction needed at all? So first, to reiterate, SS tables are immutable, and we can't just keep writing updates onto this. The disk will just fill up. And we have to get rid of obsolete data. That means data that was explicitly deleted, or it was expired using TTL, or it was just overwritten. We still need to get rid of the overwritten data. So we need compaction to reduce space amplification. Then the data itself may be scattered around in different SS tables, and we would like to consolidate it to reduce read amplification. So let's go over the fundamentals of compaction. So the first step for compaction is to select a set of SS tables to process. The algorithm that selects these SS tables is part of the compaction strategy. So different compaction strategies may have different selection criteria. Then compaction reads these SS tables and writes the compacted output onto a new SS table. Remember, SS tables are immutable. We never rewrite them. So we have to write a new SS table, which is the compacted output of those input SS tables. And while doing so, we eliminate all the overwrites, all the deleted data, and the expired data. Eventually, when this output SS table is sealed and safely stored on storage, we can finally delete the input SS tables. Okay. Note that doing this compaction requires temporary space, because we cannot delete the input SS tables until the output SS table is safe on storage. So during compaction, we will have on disk both the input SS table and the output SS table. So what can we eliminate during compaction? Let's go over a few examples. So say one SS table has a write of A into some cell, and another SS table has A prime, which is a newer version of the same cell. In this case, we just have to keep A prime, which is the newest content for this cell. If we only have one update to the cell, we just copy it onto the output SS table. If we have data into a cell and not C represents a tombstone, a deletion of this data, we still need to copy the tombstone. And that's pretty fundamental to compaction in Cassandra and in Scylla. We can't just get rid of both the data and the tombstone, because this tombstone may need to delete other data that resides on other SS tables that we haven't got to compact yet. So when can we finally get rid of tombstones? Okay, another example for just a tombstone. And the final example, it's this node Z. Node Z represents a droppable tombstone. A tombstone which was already expired. And this way we can get rid of the tombstone and not copy it onto the output. So the tombstones are kept around for what we call the GC grace seconds configuration option. And that allows us to garbage collect other data. And when that expires, we can get rid of the tombstone. Then let's talk about legacy compaction strategies before introducing incremental compaction. So the first one of the most common compaction strategies is called size-tiered compaction strategy, or STCS in short. The basics of size-tiered compaction strategy is that it organizes SS tables into tiers. So each tier has exponentially larger SS tables than the previous tier. So in this example, the SS tables in tier 2 are 4 times as large as those in tier 1. And in tier 3, we'll have it will be 16 times as large as in tier 1. And we organize the SS tables into these tiers based on their size. Now, when we compact several SS tables from a specific or some tier, we create a single SS table that's the union, the compacted union of all input SS tables. Now, if there were no deletions of duplicated data, then the union will be just the sum of the sizes of the input SS tables, and this output SS table will just become part of the next tier, but it could be also much smaller. Sorry. It could be also much smaller if we deleted most of the data, and then it could be written into a lower tier. So SS tables don't necessarily advance through the tiers. Depends on the workload. So the attributes of STCS is the worst thing about it is that it requires temporary space to compact the data, which is at least twice the data size. As I explained before, we can't delete the input SS tables until we wrote the output SS table. And while doing so, the data may be replicated, both in the input SS tables and the output SS tables. And this is part of the space amplifications. So the main factors for space amplification are first the temporary space problem that I just described, and then the accumulation of updates and deletes across the different tiers. So if like an early version of a cell resides in the highest tier, and we have a new version in a low tier, we can't compact them together until they arrive at the same tier with STCS. Another legacy compaction strategy is LCS, which is a leveled compaction strategy coming from LevelDB. And then in LCS, compaction is triggered when a level grows and has more than 10 to the I SS tables. And then SS table picks like this extra SS table from one of the levels, and it compacts it together with the SS tables in the next level, creating a new run of SS tables. Now, the set of SS tables that it selects based on the overlapping keys with the input SS tables. So it uses the Bloom factor to locate the SS tables it compacts together with this single SS table. Note that the output is a run of SS table. It's not a single large SS table as with STCS, but it's comprised of a run of SS tables. This is important because we adopted this trait of LCS into ICS. So while LCS limits space amplification, it results in higher write amplification because we have to keep rewriting the data multiple times across the levels. And that's the downside of using LCS. That brings us to the incremental compaction strategy. In a nutshell, we observed problems with the legacy compaction strategies. So STCS, size-tiered compaction strategies, has high space amplification and relatively low write amplification, while LCS has high write amplification and low space amplification. And we just wanted to benefit from both approaches. So we borrowed the SS-table runs concept from LCS and applied it over the size tiers of STCS. We merely replaced the increasingly larger SS tables with increasingly longer SS table runs. So for each SS table in STCS, we'll have a corresponding SS table run in ICS. Let's talk a bit about what are SS table runs. So first are an extension of the SS table concept. They are also sorted like a single SS table, but they are comprised of a sorted set of SS tables. And the SS tables in this set are non-overlapping. So each one has its own set of partition keys, and they don't overlap. And we call these singular SS tables fragments. So a run is equivalent to a large SS table, just split into smaller SS tables. So in this example where we have a single SS table consisting of these partition keys, it will be split into a run of SS tables, each one holding a subset of the keys of the single SS table. So how ICS works with these runs? Remember that the fragments are disjoint. They have no shared keys, and they are sorted with respect to each other. So that allows us to scan the runs that we are compacting together and compact them incrementally. So for example, we take the first fragment and write an output fragment that's the compaction of these two fragments. And when doing so, we can delete these fragments, and so on and so forth. The important part is that we can eliminate the fragments as soon as we compact them. Now, in contrast to STCS, this allows us to free up space gradually as we go. That's the main secret behind ICS. Sorry? Okay, so just presenting a case study we did in our labs. So the benchmark has 3 phases. The first phase, we just write 500 gigabytes of unique data. And when doing so, we see the space amplification overhead of STCS here in green, while the space amplification with ICS is barely noticeable. It's really in the noise. Then the next phase rewrites over and over again about half the data size, so 250 gigabytes are being rewritten all over again. And again, we see the benefits of ICS here in purple versus STCS that has these high peaks. Eventually, the third phase, the final phase, we run major compaction on the data, which will take down the data set back to 500 gigabytes of unique data. And we see this very high peak with STCS, which goes, actually, it's almost 1.5 terabytes in size, which is almost 3 times the data size. While with ICS, space drops down rapidly into the net size of the data. So that's the bottom line for ICS. It shows that we improved space amplification, and we got rid of these high peaks. And that allows you to run in a much higher utilization. So we could recommend running at like 80% of your disk space versus the recommendation to run at 50% with STCS. So that concludes my presentation. Thank you very much.